Okay, in this mini lecture, we're going to do an example of Newton's second law, looking at what is the net force acting on an object at both the magnitude and its direction, because remember, force is a vector. So let's say that we have an object. Let's say our object, I kind of am in apple mode. I guess it's because of the fall season outside. We have an object that's an apple. So here's the apple. We're going to apply a number of different forces on that apple. Let's say that there is a force acting on the apple in the downward direction. And we'll say that force has a magnitude of 3 newtons. All right. Well, there's another force pulling up on part of the stem of the apple. Let's say that it's pulling up and to the right at an angle. I'll use blue, of 50 degrees. And that force has a magnitude of 2 newtons. And finally, let's say something is pushing the apple down and to the left with a force of 1 newton, and it's pushing down and to the left at an angle with respect to the negative y-axis of 20 degrees. So there is our 3 forces acting on this apple. Okay, so how do I get the net force so that I can understand the apple's acceleration, for example? What is the net force? How big is it? How strong is it? And what direction is it acting in? Well, remember, net force is simply the sum of all the forces. Well, I have 3 forces. So let's identify them as force number 1, force number 2, and force number 3. These are vectors, and so now I just have to do a vector addition like we learned in chapter 3. So I'm going to add these vectors together to get the net force and its direction. When I add vectors together, I break them up into horizontal and vertical components. Because if I'm looking at just things acting in a single dimension, either just horizontally or just vertically, well, then I can add numbers together. So let's do that. The process I'm going to suggest that you do is identify the forces as we have here, numbering them 1 through however many forces are acting on an object. Then we can consider those as vectors, vector 1, vector 2, vector 3. And we can look at both the horizontal and the vertical components of those vectors. Very similar to the process we did when we were just doing vector algebra as a technical element. All right, so let's look at vector 1. Vector 1 is pointing straight down with a magnitude of 3. Does it have a horizontal component? Is there any to the right or to the left element of how I might describe that vector? No, there isn't. So the horizontal component of vector 1 is 0. And what about the vertical component? Now here's where you're going to have to choose the method of vector analysis that works the best for you. You want to make sure that you're representing both the component's direction and magnitude. In this case, the vector is pointing purely vertical, and it's pointing in the downward direction. So the magnitude of that vector is going to be 3 newtons, and the downward direction tells us that that value is negative. So we want to make sure that we're always paying attention to our positives and negatives, because they influence, of course, the algebraic sum. All right, vector number 2. Vector number 2 has both a to the right and up component. So let's look at those independently, horizontally and vertically. Here is the horizontal component for vector 2. And oops, that's a little long. And here is our vertical component for vector 2. I have an angle of 50 degrees. The horizontal component is adjacent to that 50 degrees. So my horizontal component of vector 2 will be 2 times the cosine of 50. So horizontally, that magnitude is 2 cosine of 50, 1.29 newtons. I always want to check if it's positive or negative. It's pointing to the right. This should be a positive value. It also has an up component, a vertical component. In this example, the vertical component is opposite my angle, so my vertical component will be 2 times the sine of 50 degrees. So the vertical component is 1.53 newtons, and I want to check if it's positive or negative. Indeed, it should be positive, and it is positive. Now, because I used an angle with respect to the positive x-axis, I could also have thought about this as, well, it's positive x-axis angle, cosine is always horizontal, sine is always vertical, and then the positive and minus will come out appropriately for my calculator. So whatever method you've been using, it's fine, but we want to make sure we're double checking our work. All right, what about vector number 3? That's contributing to the net force on this object as well. So vector number 3, my angle is given 20 degrees down and to the left. That's with respect to the negative x-axis. So for my horizontal component, here's my horizontal component that is adjacent to my angle of 20 degrees. So I will use 1 times the cosine of 20 to get my value. And I find that that's 0.94 newtons. Do I expect it to be positive or negative? Is this vector pointing to the left? Yeah, it is. So I have to be explicit about identifying the physics relevance of that negative sign. And I need to put it in. Because I'm using an interior angle, not referencing it to the positive x-axis, I need to make sure that I pay attention and confirm my physics with the mathematical relationship that comes out of my calculator. It's not the only way to do it. We could have done an angle of 200 degrees. And if I plugged in cosine of 200 degrees, it would have told me it was negative to begin with. So whatever way you want to do it is fine. Vertically, we have 1 times the sine of 20. That gives us 0.34 newtons. Again, I have to check that direction. Is it positive or negative? It's pointing down. It's going to be negative. All right. Make sure you're always looking at that direction. Now I have all my horizontal components of the net force and all my vertical components of the net force. Since they're independent, algebraically, in our vector algebra methods, I can add them together. So I'm going to add together all of the horizontal components. I have 0 plus 1.29 plus a negative 0.94. And I find that my horizontal component for this net vector is 0.35 newtons. Let's look at our vertical component. Negative 3 plus 1.53 plus a negative 0.34. I find that my vertical components add to negative 1.81 newtons. So my net force acting on this object has both a horizontal and a vertical component. How will that look? Well, the horizontal component is positive of 0.35. And the vertical component is negative 1.81. So if I use my graphical analysis of two vectors, in this case they're component vectors, adding together, this will be my net force. So how do I get that magnitude and direction? Well, I use my tools for trigonometry. So to get the magnitude of the net force, we're going to take the square root of the vertical component squared, the y direction. Oh, sorry, we're going to use v for vertical. The vertical plus the component of that net force that is horizontal, and take the square root of that. So the square root of negative 1.81 squared plus 0.35 squared. That gives me an error. What did I do wrong? I'm not sure it worked. We'll quit. I'll just do it again. So we have the square root. I'm totally doing this one on the fly. So I get 1.84 for a magnitude. So it is magnitude of 1.84 newtons. We also have to determine our angle at which that force is acting. And remember, that is the inverse tangent of the vertical component divided by the horizontal component. So our inverse tangent of negative 1.81 divided by 0.35. That gives us an angle of negative 79 degrees. Now we have to think about, does that make physical sense? Well, an angle of negative 79 degrees tells us that we're in the fourth quadrant. A fourth quadrant should have a positive x component, positive horizontal, and a negative vertical component. My components indeed match that, so I don't have to do anything with that angle. It is an accurate representation of the angle of my net force. And so I've determined the net force acting on that apple. So the change in the motion for that apple is going to depend on its mass, and that change is going to be occurring at the angle of negative 79 degrees. All right, so there's an example of how we apply the net force idea, how a net force looks visually, and how we get that value of the net force. Then we're going to be able to use it to solve some really fun problems in motion. All right, good job.